All right, let's spend a little time thinking about these somewhat more detailed um, strategies that enzymes use to stabilize transition states or help facilitate transition states to make chemical reactions reach equilibrium faster. And if the energetic bias, like I pointed out last time, is right, make the product you want much, much faster than it would form spontaneously. Okay, so we can sort of roughly categorize these in about 6 different varieties, right? The first is so-called acid-base catalysis. Um, the second is covalent catalysis. The third is metal ion catalysis. Fourth, electrostatic catalysis. These two are frequently metal ion, lots of types of metal ion catalysis are also electrostatic. I'll point that out when we get to that. Then there's the idea of proximity and orientation. This is a really important general idea. And finally, preferential transition state stabilization. It's basically the idea here is all kinds of other aspects of stabilizing transition state that don't fit in these other categories can kind of all be lumped together into this last category. Okay, and we're going to go through these with some examples one by one. We're going to go in this video, we're going to go through these first 3, right? Okay, so acid-base catalysis. Now you guys think back, maybe you remember a little bit about your basic acid-base chemistry. We've talked about weak acid, weak base equilibria, pH, right? Turns out exploiting the ability of certain weak acids and weak bases to donate or take up protons is an incredibly effective way to recognize certain features in the transition state of important reactions and get them to go a whole lot faster, right? In the case of acid-base catalysis, what we're talking about, again, is either transfer or partial proton transfer from a Bronsted acid or abstraction or partial abstraction of a proton from a Bronsted base, right? And this can really dramatically speed up a transition state if it neutralizes or creates a charge in just the right place at the right time, right? So this is a really good common example. Imagine, a simple ketone, right? So with a methyl ketone group here, right? We got a carbonyl group, right? And then a methyl group hanging off the side of it, right? Now, you guys may remember from your organic chemistry that ketone groups have sort of a isomer, right? Known as an enol, in which you now take the carbonyl group, right? You convert that into an alcohol, and you create this carbon-carbon double bond between the carbonyl carbon and what was a methyl and is now a methylene with the carbon-carbon double bond, right? Or CH2 group with the carbon-carbon double bond. But to do that, you got to pull that proton off that methyl group that's alpha to that carbonyl group, right? Shove the electrons into that carbon-carbon double bond. The oxygen's reasonably electrophilic, so you can push the electrons out of the carbonyl double bond up into the oxygen. And if you protonate that, you'll get this enol. All right, great, hunky-dory. There's only one problem, that the transition state for doing that is pretty unfavorable, right? To do that, you've got to simultaneously create partial charge on that oxygen, this sort of partially charged nascent oxyanion. You have to create this nascent negative charge, partial negative charge on that methyl group, so this creates sort of a partial carbanion. Those charges are real near each other, making that carbanion hard to begin with, right? And you've got to go through this state in order to get the enol. So this is high energy and unfavorable, and yet it's an essential reaction for all kinds of basic chemistry. We're going to see this keto-enol tautomerization over and over and over again in multiple different guises as we go through some of the critical reactions of intermediary metabolism. So there's got to be a way to do it, because if you can't do it, you can't do things like hydrolyzed peptide bonds or ester bonds, which are just common chemistry all over biochemistry. Reactions of phosphate groups require, in many cases, keto-enol-like transitions. Tautomerizations that involve group rearrangements are essential, essentially follow this basic chemistry. Group additions to carbonyl groups often involve this keto-enol tautomerization, right? So this is really freaking important stuff. But it turns out simple acid-base catalysis can make this go a lot better, right? Turns out that you can either protonate in one place or help deprotonate in another place. And in many cases, the real power is the 1-2 punch of doing both and get this reaction to go quite a bit faster, right? So here's a general acid solution to this problem, which is to basically have a weak acid positioned in just the right place, right? Nearby, real close, so that when this proton gets pulled off, and remember, pulling that proton off that methyl group that's alpha to that carbonyl group, that's not easy, right? pK of that, whoops, oh no, I lost my, hey, County, you stupid. The pK for that proton, alpha to that carbonyl group, is around 17 or so, 17, 18, something like that, which seems huge and like impossible. But if you compare it to an aliphatic, like a real sort of like methyl group, the pK of that proton, that's like something like 55, right? You're never getting that proton off of that methyl group except in something like a cracking reactor at stupid high pressures and temperatures and pHs and whatever, right? Like you're breaking up hydrocarbons in a petrochemical plant. Biology has a really hard time figuring out a way to ever get that energy barrier low enough. But this one, that one's not too bad. That's accessible, right? All right, so how do you do it, right? So get rid of all that scribbles there. So the general acid solution to this problem is to, like I said, have an acid, weak acid positioned nearby, so that if this proton gets pulled, right, maybe low probability, pK 17, but you know, maybe some possibility of this, particularly if you make formation of that oxyanion a whole lot easier. Specifically, you cancel some of that charge. You have a proton ready to go from an electronegative group that's ready to donate, maybe already hydrogen bonding and ready to donate that proton to that oxygen to form that nascent enol alcohol. That makes removing that proton way easier, right? Because now getting through this transition state is much lower in energy because you've canceled that charge with that proton ready to go and formed that enol alcohol. Okay, there's another way to do it. And in this case, like I said, you can do it by base catalysis. So if you had a good base positioned nearby that methyl proton, you're ready to like really facilitate its removal in a big way, right? You don't have to just depend on it to spontaneously pop off at neutral pH. You've got a base there with some significant electron withdrawing potential ready to pull this guy away. And again, it would never get it away from, say, an aliphatic methyl group, but this guy's pK is lower, it's accessible. And if you now can facilitate, right, that removal, because you've got this electrophilic sink over here in this carbonyl, having that base nearby has a much greater chance of pulling that proton off, right? And now stabilizing the formation of that enolate-like transition state by basically providing an energetic potential where the proton can go, right? You find something nearby that can take it up and help pull this equilibrium in this direction and lower the energy of that transition state. And like I said, the real power for doing something like this is to use both, right? You have a keto-enol tautomerization you need to have. The enzyme will then have both a weak acid and a weak base positioned in both positions, and you hit it, you double fist it, right? You both stabilize formation of the oxyanion, facilitate removal of the proton, and you can really make these reactions go much faster, much more efficiently. Okay, so that's an example of acid-base catalysis. Second category we talked about was this idea of covalent catalysis, right? So covalent catalysis is a type of catalysis where the enzyme itself directly or with a prosthetic group is going to basically form an adduct. It's going to make a covalent adduct with the substrate molecule that's going to be modified. And the formation of that covalent adduct is part and parcel of what drops that transition state for energy barrier dramatically. And then as the reaction resolves, the catalyst then gets regenerated, right? The temporary covalent bond gets cleaved, the catalyst is regenerated, and we've run the reaction. Right, so here's another example of a process, or here's an example of a process like that, where formation of a covalent bond between, say, an enzyme functional group dramatically lowers that transition state barrier, right? Okay, so here's a molecule, acetoacetate, All right. This is a category of molecule known as a beta keto acid because we have a ketone group here that is beta to this acid group, right? So it's a beta keto acid. You're going to see these guys in other contexts, beta and alpha keto acids. And they're super important because there are carboxylation and decarboxylation reactions that involve alpha and beta keto acids that are super important in basic biochemistry. And that's exactly what's going on here, right? So acetoacetate will decarboxylate to form acetone, right, by loss of gaseous CO2. So in this case, if you can get the electrons that are over here in this acid group and you can drive those into that carbon-oxygen bond, to form another carbon-oxygen double bond, and provided you have somewhere for the electrons in that methylene carbon bond, or the methylene to the acid carbon, you have somewhere for those guys to go, you can drive this reaction, right? And it turns out that ketone group, kind of like we saw with keto-enol tautomerizations, that carbonyl group's a pretty good electrophilic center, right? It's not too bad. So you can split that bond, shove those electrons over here to form this enolate, this enol-like intermediate, ram those electrons up into the oxygen to form this oxyanion. If you protonated it, you get an enol, but for these reactions, you often don't. It stays this oxyanion. And you get this so-called enolate, right? It's a deprotonated version of an enol, right? Decay of that intermediate, this is the transition state for this reaction. All right, decay of this transition state by moving those electrons back to reform the carbonyl, the ketone group, then generates the product acetone. All right, so that decarboxylation reaction occurs on its own reasonably well. Beta keto acids will decarboxylate to some extent spontaneously, way faster than other types of alpha keto acids. Basically don't spontaneously very well at all. Beta keto acids will, but it's pretty slow. And it's pretty slow because formation of this enolate intermediate, right, this oxyanion intermediate, it's energetically difficult to do, right? It's not a simple thing to do, which makes this reaction proceed pretty slowly. Now, there's a fairly straightforward way to enhance this reaction, and that is to jack up the electrophilicity of the group that needs to suck up those electrons when you cleave that methylene acid carbon bond. And it turns out one of the ways to do that is to use an activated primary amine. If you remember your basic organic chemistry, activated primary amines will react under the right conditions with carbonyl groups in ketones and aldehydes to form a carbon-nitrogen double bond compound, right? In this case, it was a primary amine, right? So I said it's a primary amine. You use a proton, you lose the alcohol from the carbonyl group and release hydroxyl to form this carbon-nitrogen double bond, or so-called imine, right? Now, because you've got a nitrogen with 4 bonds, right? You have this the electronic structure of this molecule has this orbital that's readily accessible. So this so-called Schiff's base is for the guy who first discovered these, is an incredibly good electrophilic center, right? So you can now easily pull these electrons over. Now it's almost trivial to cleave this bond because those electrons have a really happy place to go. They can flow right in to forming this enolate-like intermediate state, but the electrons that would have been in that carbonyl to have to go up and form that oxyanion, now they flow right up into that unoccupied orbital, that positively charged Schiff's base, to form the neutral nitrogen analog of the Schiff's base, because it's incredibly nice, deep electrophilic sink, right? That's great. And this dramatically stabilizes this state compared to that isolated enolate. Now, to reverse this, all you got to do, push those electrons back down, push these guys back over, reform the Schiff's base, come in with a little hydroxyl ion to now kick off that primary amine, and you've now covalently catalyzed the decarboxylation of that beta keto acid by forming a temporary adduct with this primary amine that dramatically lowers the energy of this transition state, right? Okay, might be worth thinking about, what amino acid do you think maybe would be really good at doing this? You think about that one. Okay. Now, covalent catalysis sometimes gets categorized in a couple of different categories as either electrophilic or nucleophilic covalent catalysis or electrophilic covalent catalysis. The general scheme for covalent catalysis frequently sort of follows this same basic sort of schema where you have sort of nucleophilic attack of the catalyst on the substrate, right? Followed then by electron withdrawal by the now electrophilic catalyst, followed then by elimination of the catalyst. And so that's sort of this three-step tango that describes most covalent catalysis. Right. And the distinctions between whether it's electrophilic or nucleophilic, it's kind of fuzzy, but in general, a nucleophilic covalent catalysis describes a situation where this step, the nucleophilic attack step, is limiting. This is rate limiting, right? Whereas electrophilic catalysis, nucleophilic catalysis, or electrophilic covalent catalysis would involve this step being rate limiting, right? The electron withdrawing step, right? So it doesn't necessarily matter for our purposes, but you may hear things categorized that way sometimes, right? So covalent catalysis is this incredibly important type of catalysis that we're going to see some general multiple versions of. Okay, so metal ion and electrostatic catalysis. Like I said, these are kind of related in some ways in which metals get used. Let's talk about the sort of metal ion catalysis first. Metal ions are, as you probably know, incredibly common and incredibly important for catalysis in biochemistry, right? Roughly, I think my memory is that somewhere in the range of about 1/3 of all enzymes have an associated metal or depend upon a metal at some level, right? So that's a lot. That number may have gone up. That's the number that's stuck in my head. And there are two rough different classifications of metal-dependent enzymes. You have so-called metalloenzymes, in which the metal is important for catalysis, but it's also essentially a structural feature of the enzyme itself. So if you take the metal away, the protein, the enzyme is basically not only inactive, it's unstable, right? You lose structure. So they're like incredibly important, integrally structural elements of the enzyme itself. You almost can't talk about the enzyme in the absence of the metal. It's a structural element of the enzyme as well as being important for aspects of the catalysis. And a lot of enzymes, these kinds of enzymes that use, oh geez, come on. Metal ions, or I should say metalloenzymes, stop. Why are you doing that to me? All right. So the metalloenzymes often use metals like iron, iron 2, iron 3, zinc is common, copper, right? Metals, these aren't always used in enzymes that you would call metalloenzymes, cobalt, right? But frequently when an enzyme uses one of those metals, it's a metalloenzyme, right? It's important not just for the catalysis, but for the structure and stability of the enzyme itself. Then you also have a so-called metal activated enzymes. And in this case, the enzymatic activity of the enzyme requires the metal, but you can strip the metal away and the protein's basically just fine. It just won't do chemistry without the metal, right? And these enzymes often depend upon metals like sodium, potassium, magnesium, calcium, for example, right? Okay, so we got these two different categories of enzymes that depend upon metals. All right, let me see if I can erase this. Maybe it'll be, if I just do, oh no, now I've queued up, there we go. I said make it go away quickly. All right, now, whoops. All right, so what do the metals do in the case of these enzymes? And there are several different things that metals can be used for when you start talking about an enzyme. In some cases, you have a substrate molecule with interacting groups that is not going to get positioned right in the binding pocket of the enzyme without the metal, right? So the metal directly interacts with the substrate in a way that governs the binding stability and or orientation of the enzyme in the right way in the active site in the binding pocket of the enzyme. That's pretty common. Another one where these are really, really common is doing redox chemistry. Some of the amino acids, cysteine is a really good example, can do some types of redox chemistry, but there's a gigantic range of redox chemistry that's basically impossible to do with just the functional groups on amino acid side chains. And that's where metals really come in to biochemistry in a big way, is doing oxidation and reduction reactions that you just can't do if you don't have the chemistry available, sort of the organometallic chemistry available with the way in which these metals interact with electrons and their oxidation and reduction states, right? Another really common way, and this is where we have this sort of overlap between metal ion electrostatic catalysis, is metals, because they're generally positively charged, right, can stabilize the development of negative charge in a transition state of a reaction in incredibly effective ways, right? So if you have like a 2+, 3+ ion of a metal, that's a lot of positive charge in a very small space, right? So you can use that to shield or reduce the development of critical negative charge in a transition state massively, right? So this is a situation where you would formally call this electrostatic catalysis, because that's what the metal is doing. And I sort of mush these up together because you could do the same thing with side chains, right? So if you needed to reduce some negative charge, you could do it with a metal, or you could do it with some positively charged amino acid side chains, right? Like a protonated histidine or a lysine or an arginine. And you can do the same thing in the other direction by using negative charge states of, say, acidic amino acids like aspartate and glutamate if you needed to stabilize some positive charge, right? So stabilizing the development of an unfavorable charge distribution in a molecule is basically generally referred to as electrostatic catalysis. And you can either do it with metals or the amino acid side chains alone. As here's an example of one of these. We haven't talked about these kind of enzymes yet, but you have an enzyme like carboxypeptidase. This is an enzyme that's going to cut polypeptide bonds. It's got an active site alcohol group. It's on a serine residue, and that active site residue is going to attack that carbonyl carbon to split this amide bond. But to do that, when that nucleophilic attack happens, the electrons in the carbon-carbon double bond of the carbonyl group have to go somewhere, and they're going to flow up into that oxygen to form a so-called oxyanion. Well, formation of that oxyanion, like we just talked about, is not so favorable. If this sort of negative charge building up on a molecule, would really rather not have it there. It would really rather come back down here, regenerate the carbonyl. But you can stabilize that if you have some positive charge up there that interacts favorably with the oxyanion. And carboxypeptidase does that with a strategically positioned zinc ion. That's absolutely critical. You take away the zinc ion, carboxypeptidase doesn't work very well. And it stabilizes formation of that oxyanion in the so-called tetrahedral intermediate, and dramatically increases the rate at which carboxypeptidase can cut peptide bonds. Okay, in the next video, we'll take up some of these other strategies that sort of bridge out a little bit more in other ways that enzymes stabilize transition states.